The next three sections that we'll be looking at will all be based on solving systems of equations. The first way that we're going to look at it is solving systems by graphing. Then we're going to look at solving them by substitution, and then by the addition-elimination method. So where we begin is with understanding the idea of what a system is and whether or not an ordered pair satisfies that system. Then we're going to use graphing to solve the systems. We're going to talk about what makes a system inconsistent versus dependent. And then we're going to look at a system and say, is this dependent, inconsistent, or consistent? And be able to tell, looking at a formula in proper y equals mx plus b form, which of the three situations I have. So we're going to look at whether a given ordered pair is a solution to a system by looking at a couple equations. So here's an equation, x plus y equals 3. Here are some points that are solutions to this equation. 0 plus 3 equals 3, so the point x equals 0, y equals 3 is a solution to this particular equation. 1 plus 2 equals 3, so 1, 2 is a solution. 2, 1, 3, 0. Here are 4 possible solutions. There's infinitely many solutions that we can put together. Now we have a different equation, x minus y equals 1. Again, we can plug in and show 0 minus a negative 1. Minus a negative means plus, so 0 plus 1 equals 1. 1 minus 0 equals 1. 2 minus 1 equals 1. 3 minus 2 equals 1. So in any of these cases, if we took x, plugged it in where we see an x, took y, plugged it in where we see a y, we'd end up with a true statement where this side would equal to 1 if we chose any of these xy pairs from the list. Thinking back to our previous table when we were doing a different equation, x plus y equals 3, this solution, 2, 1, fit that equation as well as this new equation. So really what we're doing when we have a systems of equations is we have two distinct formulas. We're looking for the one solution that satisfies both formulas. So the way that you're going to see these when they're asked in the online system is you're going to see this brace symbol. That brace means these two equations are related. It's really set notation it's usually used for, but it's basically saying think of these as a system of equations where you're looking for a solution that satisfies not only the first equation but also the second equation. So because the ordered pair 2, 1 was a solution to each of the two equations independently, we say that it satisfies both equations, therefore it's a solution to the system of equations. In general, a system of linear equations can have exactly one solution, no solution, or infinitely many solutions. We're going to mostly be working with ones that only have one solution, but you will need to be able to identify when the special situations occur, where either we have no possible way that we can have the two lines meet, or we have basically the same line where any solution would work as long as it's on the line. So this asks us to determine whether negative 2, 5 is a solution to each system of equations. So really what that's asking is negative 2, 5 a solution to each individual equation within the brace system? So what we're going to do first is take this negative 2 for x, plug it in here, take this 5 for y, plug it in here, see if we get a true statement. We're then going to do the same thing for the second one, see if we get a true statement. If both are true, in that case, yes, it satisfies and it's a solution to the system. Same idea, we're going to take negative 2, 5, plug it in here, plug it in here. If both are true, then yes, it satisfies. So starting with the first one, we originally had the equation 3x plus 2y equals 4. We want to put negative 2 in where we see an x. We want to put 5 in where we see a y. 3 times negative 2 plus 2 times 5. 3 times negative 2 is negative 6. 2 times 5 is 10. When I combine negative 6 and 10, I do get a positive 4. So you'll see there's this question mark here, basically saying, even though it's an equality, we don't know if the point we plugged in really is going to make it equal or not. So in the end, if this question mark is true, yes, they're equal, I have the same thing on both sides. then it is a solution. If this question mark were not true, if I had something like 5 equals 4, then it would not be a solution. So it worked in the first equation. We're trying the same numbers into the second equation. Remember, we're putting negative 2 in for x, positive 5 in for y. Negative 2 minus 5 does equal negative 7. We get a true statement. Therefore, it satisfies both equations and is a solution to the first systems of equation. We now are looking at the second one, the one that was labeled B a few slides ago. So we first try it into 4y equals 18 minus x, again putting negative 2 in wherever we see an x, and 5 in wherever we see a y. Since on the right side it's a negative 2, it becomes a positive 2, so I get 18 plus 2. On the left side, 4 times 5 gives me 20. So 20 does equal 18 plus 2, really 20 equals 20. We know that we satisfied the first equation. We now try the same thing in the second equation, plugging in a 5 where we see y, plugging in a negative 2 where we see x. This gives us the equation 5 equals 2 times negative 2, 5 equals negative 4. That is not true. That tells us that this is not a solution to this particular equation, which means it can't be a solution to the overall system of equations. So here, even though it satisfied the first equation in the system, since it doesn't satisfy the second, it is not a solution. So, to use the graphing method, the general idea is we're going to put the two lines on a coordinate plane. Wherever the two lines meet is the solution to the system. So they're showing here that they're going to use the intercept method to graph. If you think back to 3.2, that's where we learned the intercept method, plugging 0 in for x, solving for y, plugging 0 in for y, solving for x. While that will work, and you can see graphically where the lines meet, I'm going to encourage you to get used to y equals mx plus b form, and to change these lines into y equals mx plus b form in order to graph them. Then once you've graphed them in y equals mx plus b form, you can find where they intersect. That said, if you just do it by plotting the two intercept points in the system in WebAssign, you should be able to see where the two lines meet, and you should be getting correct answers. Usually when I have students do this out by hand, I tell them to use the y equals lines, because that way it's kind of easier for me if they just draw their line a little off to make sure I'm giving them credit, if they have the right equations of the lines, and they were trying to make it go the right way. But truthfully, since it's all being done online now, it should line up at the right place if all you do is put in the points. So if you feel more comfortable with the intercept method, feel free to use it. This is what they get when they do the intercept method. They put in 0 for x, get back 3 for y, so they have the point 0, 3. They put in 0 for y, get back 3 for x, so they have the point 3, 0. These 2 points are graphed on the line 0, 3, 3, 0. So this purple line is from this first equation. The second equation has points 0, negative 1 when I plug in 0 for x, I get negative 1 for y. So here's 0, negative 1. When I plug in 0 for y, I get 1/3 for x. Kind of annoying to plot 1/3. I would prefer the example to have whole numbers, but that said, there is that 1/3 they've plotted, 1/3, 0. Finally, we can see where these two things meet. Right here, this purple line intersects this blue line. It's happening at the point x value 1, y value 2. So 1, 2 is the solution to the system. We can see that if we put in 1 for x, 2 for y, 1 plus 2 does equal 3. If we put in 1 for x, 2 for y, 1 times 3 equals 3, minus 2 does equal 1. So we can see that where the two graphs meet. We can figure out what that point is on the coordinate plane, and we can record it as a solution. The solution's written as an ordered pair, 1, 2, which really means x equals 1, y equals 2 is the solution to our equation. Again, this is plugging back into the equations just to see does it satisfy. You can always do this as a check to make sure you found the right point if you're not sure from your graphs whether the point really is correct. But you do not need to do this extra step. If you find where the two lines intersect and you feel good about where it is, that is the solution to the equation. So when the graphs of two equations in the system are different lines, the equations are called independent equations. So really, independent just means two different lines. Dependent would be if I have a system where I have two of the same exact line. When a system of equations has a solution, the system is called a consistent system. So a consistent system is basically any two lines that intersect at a point. We're going to see the other possibilities are inconsistent systems where two parallel lines never intersect, or dependent systems where you just have two lines drawn directly over each other. So a consistent system is where we have two lines that intersect at a single point. To solve a system of equations in two variables by graphing, first we graph each equation on the same rectangular coordinate system, and really I would say before that we put each equation into y equals mx plus b form. Then we carefully graph each equation on the same rectangular coordinate system. If the lines intersect, we determine the point of intersection. The ordered pair is the solution. We then put the solution back in to see if it works, just to make sure that yes, we found the right solution. Solve the systems of equations by graphing. So again, my way of doing this is I would say minus 2x goes over here, divide each part by 3. I'd say minus 3x goes here, minus 2y goes here, divide each part by 2, and then multiply through by a negative. So I would go through all the steps we had to do in the last unit to get things into proper y equals mx plus b form. That said, I can do this using the intercept method. If I put in 0 for x, then for y I should get 2 divided by 3. If I plug in 0 for y, then for x I should get 1. Similarly, if I plug in 0 for x, then for y I should get negative 8. If I plug in 0 for y, then for x I should get 16/3. So I think they're going to do it that way with the intercepts. Again, I don't like that we're involving these weird fractions. I did get a bunch of emails asking how to put those fractions in disengage. Just so you guys know, the way to put them in is you just graph a point that doesn't have fractions or decimals in it, then you click on the right side on the name of the point, and you can go in and edit the coordinates. And that's how you put it in as a decimal in disengage. That said, this is where we end up with our possible solutions, so that now we can put these on a graph. So you can see they plotted the points that they found. Here's the two intercepts for the purple line. Here's the two intercepts for the blue line. They then see where blue line meets purple line. It's happening at a value. X is 4, y is -2. So based on the graph, they find that solution point to be 4, -2. We can then see, does it satisfy each equation? Well, if we plug it into the first equation, 2 times 4 is 8. 3 times -2 is -6. 8 minus 6 does equal 2. So the first equation is true. In the second equation, 3 times 4 is 12. 2 times -2 is -4. -4 plus 16 is also 12. So since we have a true statement at the end, that is also a solution to the second equation. It means that that point that we found, 4, -2, is the proper solution to this system. Use graphing to identify inconsistent systems and dependent equations. So when we have an inconsistent system, what's really happening is we have two parallel lines where they have the same slope but different intercepts, and therefore will never intersect. This is a situation like that. If I were to solve out this second equation in y equals mx plus b form, I'd take this 4x to the other side and get -4x plus 8. I'd then divide by 2, and I'd get y equals -4 divided by 2 would be -2x, and then instead of plus 8, 8 divided by 2 would be 4. The key thing here is it would be a -2x, which is the same as the -2 in front of the x in the equation above. Since they both have the same number in front of the x, or they have the same m or slope, it means they're parallel lines. Because this would become +4 after being divided, and this is -6, they're not the same line. If they both had the same intercept, -6, and the same slope, -2, they'd be the same line and it'd be a different situation. But what's happening here is we have two lines with the same slope and different intercepts, which means they're just going to go on forever and never intersect. That's why it's an inconsistent system with no solution. So we'll graph both equations on the same coordinate system. So the first one they're doing by using mx plus b. The second one, instead of rearranging as I was showing, they're going to put it in using the intercept method. But what happens is what I said would happen, that I have two parallel lines, where this line has a slope of -2, and the intercept is 0, -6. This also has a slope of -2, but the intercept is 0, 4. Since they have the same slope, different intercepts, we would label the system inconsistent. If you get a question where this happens in the homework, it tells you to put in capital letters, inconsistent. Here we're seeing that if we rearrange, like I said, the second formula to y equals mx plus b, we'd see that the slope, -2, is the same. The intercept, -6 versus +4, is different. Again, that's why the system is inconsistent. Because parallel lines do not intersect, the system has no solution as inconsistent. Since the graphs are different lines, the equations of the system are independent. So, the next thing we're going to talk about is this situation. These are dependent systems when they have two lines that are exactly the same. So, the most common thing that we're going to look at, purple line, blue line intersect in exactly one point. That one point is our solution. Two different ways that are tricks, basically, that we have to be on the lookout for. If I have two lines with the same slope and different intercepts, I have to label that inconsistent, and it really means there's no solution, there's no place where we can put in an x and y that'll work in both equations. Last way is if we have literally the same exact line. So you can see that if you took this 2x plus 2y equals 4, if I move the 2x over here, I get 2y equals -2x plus 4. If I divide it by 2, I get y equals -x plus 2. This second line is exactly y equals -x plus 2. So it's when they're literally the same exact thing, same number in front of x for a slope, same number after x for an intercept. When that happens, we call it dependent because they're the same line. Dependent meaning if you tell me what x equals, I can tell you what y equals for any x value that you give me. I'll basically just plug it in here. So a solution to both of these lines, if I put in 0 for x, I get 2 for y. 0, 2 satisfies both of them. If I put in 2 for x, I get 0 for y. 2, 0 satisfies both of them. If I put in 1 for x, I get 1 for y. 1, 1 satisfies both of them. I could keep picking out any point on this line, and they would all be solutions. That's why there's infinitely many solutions when they're the same line. So if we have to identify how many solutions are in a linear system without graphing, what we're going to do is put both lines into y equals mx plus b form, look at the slope. If the slope is different, we'll stop right there and say, since they have different slopes, it's a consistent system with one solution. If the slopes are the same, there's two possibilities. Same slope, different intercept means that they're parallel lines, or it's an inconsistent system with no solution. Same slope, same intercept, it means they're the same line, or it's a dependent system with infinitely many solutions. So, if they have different slopes, they intersect, one solution. If they have the same slope, different y-intercepts, they're parallel, it's inconsistent with no solution. And if they have the same slope and same y-intercept, it's the same line, it's dependent with infinitely many solutions. Here's two equations that we start out with in order to figure out whether or not these have, or whether these have 1, 0, or infinitely many solutions. We start by putting them in y equals mx plus b form. So for the first equation, it becomes -5x plus 5. For the second equation, it becomes y equals -3/2 x plus 4. Because the -5 and the -3/2 are different, it means that these are not parallel lines, they're not the same line, therefore there is exactly one solution to this system. They will intersect at one point, and the system has one solution.